Okay, so let's actually talk about some math finally. So that was more than usual front matter, but I think hopefully it was worth it. Okay, so I want to talk about the product rule together, even though it's in the content. There's quite a bit of stuff there. This will be a little bit of a different angle on it, and I think it helps elucidate certain things about the way I want you to think about derivatives that are going to be helpful for what we're doing moving forward. Okay, so suppose we have a differentiable function f, and that we increase the input from some value t to a nearby value t plus delta t. So delta t is a small quantity that we've moved over, like let's say it's positive, we've moved over a little bit to the right. Approximately how much does the function's output change by? Cool, so a couple of answers there. Actually, I'll share a third one. So these are all correct. Yeah, so literally how much it changes by is f of t plus delta t minus f of t. So you start at f of t, and then after you make the change, you're at f of t plus delta t. So how much does that change by? You subtract. So this is exact. And I guess by putting approximately here, I was sort of pointing towards a particular simplification, which is what was pointed to by these other answers. So it's delta t times the slope at that point, and the slope is also known as a derivative. So we can say f prime of t times delta t. So this is sort of in some sense the main idea of what a derivative is. It's a scale factor to convert from small changes in input to the resulting changes in output. So if our small change in input is delta t, we need to multiply by that scale factor to get approximately the change in output. So f of t times delta t is approximately how much the function changes by when we change the input by delta t. And just an aside for people who might find it confusing, because it's most people, I think, when they first see it, an expression like delta t is a single variable name that has two characters instead of one. So it's not an operator, it's not something philosophical. It's literally just one variable name that has two characters in it. Okay, so the product rule asks what happens if you have a product of two functions f and g, and you change the input by a little bit from t to t plus delta t. So we know how f changes. It goes approximately to wherever it was before plus the amount that it changed by. And same thing for g. It was g of t before, and then it changed by approximately g prime of t times delta t. So this is going to be our new value. So originally our product function f times g starts at f of t times g of t. And then afterwards, it's going to be the product of these two things. We've got to multiply both expressions. Right? So this is what that looks like. We just say what f changed to, what g changed to, and then we multiply those things. And we're like, okay, how much change does that represent? So what happens if you look at this product, if you multiply out this expression, what's going to come next on our way to the product rule? A few answers here. I'll let Shabam talk about what he's looking at here. So yeah, that's exactly what's going to happen here. So let's break it down and illustrate sort of a way of thinking about this second order term, and that's going to be a kind of segue into Taylor series, which we'll get into next. So yeah, so what's going on here is the first term gives us f of t, g of t, which you see here in Shabam's answer. And that's the original value of the product. So that's telling us kind of where we're starting. It's good that that term shows up because then the other terms will tell us the actual change. And then the next two terms give f prime g plus g prime f times delta t. And so that's telling us that as far as these terms are concerned, we'll think about this other one later, but as far as these terms are concerned, this stuff in parentheses is the scale factor that you need to multiply delta t by in order to get the resulting change in the product function f times g. So this is already, if you remember the product rule from calculus class, this is where the product rule comes from. This is the right answer. Is we just need to think about what's going on with this last term when we multiply the f prime times delta t and g prime times delta t. So one way of thinking about this as Shubham said, is that, well, delta t is really small. That's the point of derivatives. You consider really, really small changes in input. And so delta t squared is going to be sort of way smaller, and we can just kind of neglect it. But another way of thinking about this that maybe tightens that up a little bit is that delta t squared factor, it means that if you're thinking about like, okay, what scale factor do I need to multiply delta t by to get this change? The factor you need to multiply it by still has a delta t in it. Like after you kind of factor out one delta t like we did here, there's still another delta t left. So you're like, okay, what do I need to multiply delta t by? And there's still a delta t in there. So as you take delta t smaller and smaller, this scale factor that you need for converting inputs to outputs is going to zero. This contribution is going to be smaller and smaller as you consider delta t smaller and smaller. So ultimately, it has no contribution in the limit. Whereas this part, this scale factor has no delta t in it. So as we consider smaller and smaller delta t's, we're still using exactly the same scale factor to convert inputs to outputs. So this one sticks around, whereas this one goes away. So there are lots of ways of thinking about this. You've probably seen more rigorous ones in a calculus class, and those are good too, but I'm trying to present a kind of just a different way to think about it, a little bit different notational presentation. It is all the same idea ultimately, but it's important, I think, to really nail down this idea that a derivative is a scale factor for converting from small changes in input to resulting changes in output. Incidentally, this idea of a term that has the square of the change of input in it, so it's some stuff that doesn't depend on delta t times delta t squared, that's called a second order term. And we ignore this one here for reasons I just explained, but also it's when we write down this approximation, we're already ignoring second order terms. So there's, it's approximately equal to, and that the part that makes it not exactly equal to is going to be a quantity that's expressible in terms of something times delta t squared plus maybe something times delta t cubed and so on. So there's kind of some missing stuff here to the right, which is turning this into an approximately equal to. And that's where Taylor polynomials come in. So that's what we'll talk about next. I do want to just put the figure up again from the Dei Gymnasia so that you just have a chance to see it. So you can arrange this geometrically if you want sort of to hold this in your head in a way that doesn't depend on, the notation on the page. And you can think, well, what if I change t to t plus delta t? And like my function's value, output value f, I can represent as the length of a line segment if I want. So just pretend everything here is positive for simplicity. And then how much did the function change by? Well, f prime of t times delta t. Same thing along this other axis. And then I'm visualizing all my parts. I have my f of t, g of t, that's where I started. And then how much did I change by? Well, I really added these two panels, this long rectangle and this long rectangle. And well, also this small rectangle too, but as delta t gets really small, this is going to be super tiny. And these are just going to be pretty tiny. They're going to be slender, but they'll still have one big dimension. And this one up in the top right is going to get really small in both dimensions. So that's kind of a geometric manifestation of this like second order concept. We're throwing out this little rectangle up here and we're giving something up, but it's not very much compared to the small change that we're preserving, which is the areas of these two other rectangles. And just to point out that this is another instance where the geometric picture where you're focused on the slope interpretation of derivatives doesn't really give you the insight you need. If you're plotting these functions f and g and trying to plot their product, you're not going to be able to see what's geometrically useful about this picture. We had to co-opt both axes here to plot actual output values of the function, and that left nothing over to plot input values. But that's fine because we have this idea that we can change the input a little bit sort of in our minds away from the picture and then just see what happens to the output and actually plot that. So scale factor for converting between small changes in input to resulting changes in output, that idea it's broader and it kind of gives you more leverage to use visualizations in creative ways than if you're stuck on the slope of a tangent line concept, which again is also useful and important, but you don't want that to be the only way you think about derivatives. Okay, so let's segue from there into talking about Taylor polynomials. So we'll start with this observation. So we have this this mathlet allowing us to show the graph of a line tangent to the graph of the sine function. And I think it's pretty clear here, just informally, there are certain spots where the line does a really nice job of sort of gripping the function's graph, like it's modeling the function very nicely. And there are other spots where it's always decent. You could do worse, but there's some spots where it's not as good. Okay, one answer in, 8 people still typing, so I'm gonna just let people finish up their messages. Okay, cool. So I think we haven't heard from Mark in a while. So Mark sent in this last one here, and he's got a check mark by his name. Great. Yeah, that's what's going on. And we can get a sort of, I like to point out the actual connections between visualizations and the underlying math ideas. And here's a good one. We can say something about how good the approximation is just based on the first little sliver of white that we see between the actual graphs. So these graphs, the lines take up a little space on the screen. And so they're effectively, from a math point of view, they're giving you a little buffer around the actual graph of the function. And where the colors overlap, that's telling you where the function's values are closer than that buffer, than that little amount, like the stroke thickness. And so we can see that you don't have to go very far away from 1.5 or 1.6, whatever this value is. You don't have to go very far left and right to start seeing some slivers of white in between the two graphs. Whereas if you put it here in the middle, and this, so the reason this is a little hard to control is that the graph is constantly recentering. And the reason for that is when you click the zoom button, you want it to be centered in the right spot so you don't lose the dot. But anyway, you see you have to go much farther to see some white space in between the graphs. So it's clearly fitting much better here and not as well up at the top. So, okay, so that's kind of that's my little introductory example for thinking about why you would want to step up from a linear approximation that just accounts for the derivative to thinking about, well, what next? The idea is derivatives are really helpful for thinking about certain basic questions, like, is a function increasing or decreasing? Like, you look at this function at 1 or something, and you want to know, is it increasing or decreasing right there? Well, I mean, it's pretty clear just from the graph that it's increasing, but if you didn't know, you could zoom in, and the definition of the derivative ensures, this is another connection between the visualization and the actual math. The definition of derivative ensures that this is always what you're going to get. If you zoom in far enough on the graph of a function, then the line in the graph of the function are going to look totally superimposed at a particular finite pixel density at some sufficient level of zoom. There's no telling how far you have to zoom in to make it happen, but at some zoom level, you're going to have this picture. And then intuitively, it's very clear that if this is what the graph looks like zoomed in far enough in, it has to be an increasing function at this point. There's no way the function is dipping down a little bit if you can always zoom in and it always looks exactly like this. So it is a little bit difficult to make a mathematical proof totally out of this visualization thing, but the visualization is actually rigorous. You can make sort of formalize the idea of a screen and pixels and whatnot. And a function being differentiable at a point means exactly that. At some zoom level, and all zoom levels there past, it's going to pixel for pixel be the same as the line that's passing through that point with an appropriate slope. Okay, so anyway, that's what's valuable about linear approximations, but you can kind of lose that value to some extent if you, for example, you're at a maximum, the slope is going to be 0 already, and you want to know something more than that. You want to know, does it curl down or does it curl up? That's a really important question in applied math. And your first derivative is not going to tell you that, because the first derivative just tells you it's flat. So that's what we're going to try to figure out with Taylor series. And the idea is, okay, what's the next thing up from linear functions? Quadratic functions. And those are also pretty simple, just squaring a number. We've got some multiplications and additions. Compared to what can happen in general with a function, this is pretty basic. And that's going to be helpful, because maybe we can take something more complicated and break it down into something more basic. So let's actually see what this looks like before we get into how to do it. So what we're going to do is take the polynomial of degree 2, so the quadratic polynomial, which does the best job of fitting the function's graph locally. And what we see when we do that is that the fit is way better than when we had a line. Kind of in general. Not quite everywhere, because it actually is a straight line. So the best polynomial of degree 2 or less is a linear polynomial at the origin. But as soon as we move away from the origin, we start to get a little bit of curl in that orange graph. And it's going to fit the function's graph better at the point of interest than a straight line would. All right, so we can see that this does a nicer job at the cost of a little bit of additional complexity and keeping track of, like, you know, an extra term for this orange function. So here's an exercise, well timed because it's been too long. So find the derivative of this function at the origin. So it's just a generic quadratic polynomial, a0 plus a1t plus a2 t squared. So a0, a1, and a2 are just names for the coefficients of the constant term, the linear term, and the quadratic term. And we just want to differentiate it at the origin. Okay, great. So yeah, so the derivative of this function is a1 plus 2a2 times t, which at the origin is just equal to a1. So this is an important, it seems like a pretty basic exercise, but it's an important idea. When you differentiate a polynomial and evaluate it at the origin, this cool thing happens where the constant term goes away, and then everything past the linear term also goes away because it's still going to have a t in it. So when you substitute t equals 0, then that part's going to go away. So what you're left with is the linear term. So let's take that up one level and see what happens there. So what about the second derivative at the origin? So if I just differentiate one more time and substitute t equals 0, what do I get? I'm making sure the timer has a chance to get all the way to 0. I don't want to cut people off early, but people were getting that very quickly, which is good. Okay, so again, it seems like a pretty simple exercise, but actually doing the exercise helps you appreciate what's going on. When you differentiate a polynomial at the origin some number of times, then you really get to isolate one of the terms, because every term to the left of the one that survives gets wiped out from the differentiation, and everything to the right gets wiped out by the substitution of t equals 0. So, okay, there's this extra factor of 2 out front, but basically it just a2 is just giving us direct information about the second derivative of this function. So if we want the first order and second order derivatives of this polynomial to match those of any function f that we can differentiate repeatedly, then we need to let a0 be f of 0, so that the actual value matches, the 0th order derivative matches. We need to let a1 be f prime of 0, because we decided that the first derivative at the origin is a1. And the coefficient of t squared needs to be 1/2 f double prime of 0, because that way, when you differentiate this polynomial twice, you get 2a2. So we decided a2 should be half f double prime. That 2 cancels that 1/2. And you're left with f double prime at the origin equaling the second derivative of this polynomial at the origin. So f here is not the polynomial. F is just some function that we can differentiate repeatedly, and the polynomial is something that's supposed to approximate it. So just this little fact about how repeatedly differentiating and then substituting t equals 0, that isolates a particular coefficient, that allows us to just take those derivatives of our function and string them along as coefficients of a polynomial, with this extra factor that we need to kind of make things work out nicely. And then we're going to get a polynomial which approximates our function as well as possible, in the sense that its derivatives match as much as possible. Its value, its first derivative, its second derivative. If we want to include more terms, so we just continue in that way. All right, so when you see this formula, I think it is maybe a little hard to remember it long term, but the simpler idea is just match derivatives. Everything follows from that. So you can go back and differentiate a generic looking polynomial and then set the coefficients to be what they have to be, so that the first derivative of this function is f prime, the second derivative is f double prime, and so on. But this function f is going to have actual derivatives at the origin. So these are all going to be numbers. So we're going to have number plus number times t plus number times t squared. That's just a plain polynomial. So it's no big deal from a computational point of view. You can do whatever you need to with it. Okay, so just to give an example here, if you look at a function like cosine, its value at the origin is 1. Cosine of 0 is 1. Derivative of cosine is minus sine. That's 0. So the linear term is going to be 0. And the second derivative at the origin is minus 1. So the Taylor series is going to be 1 plus 0 times t plus 1/2 times minus 1 times t squared. So that works out to 1 minus t squared. And we can plot this. I'll give you some Python code, although we haven't started our Python session, so it's going to take a while to run. But this is sort of a kind of minimal example for getting up a quick plot in Python. You're going to import the plot function. Import, I think linspace is kind of the nicest way to give yourself a range. So you can say linspace -3 to 3, comma 100. That gives you 100 values starting at -3 and ending at 3, equally spaced. And you can use those to do your plotting. You take the cosine of each of those values, apply this polynomial to each of those values. So all of these operations are automatically operating entry by entry for each value in X. And then we just do 2 plot calls in the same cell, and matplotlib knows that we want those to appear on the same graph. So we'll get both of these things superimposed. Yeah, so I'll just kind of show you what happens when you go beyond that. So you'll have this in mind. So I'll ask a question and then immediately answer it. So if we throw in a third term, a3t cubed, and then differentiate that 3 times, then again, we're going to get just this one coefficient, this new coefficient we added, and it's going to have a factor of 6 out front because the 3 comes down when we differentiate the first time, then a 2, then a 1. So we get 3 times 2 times 1, which is 6. So if we, yeah, there's a graph that popped up. So we can see we did a pretty nice job right around the origin approximating the cosine function. But anyway, if we want the third derivative of our function to match the third derivative of this polynomial, then we have this equation to solve. 6a3 equals f triple prime, which tells us what a3 has to be. And in general, we can say that the nth term is going to be the nth derivative of the function we're trying to approximate divided by n factorial. And n factorial is just the thing that we just got. You have a factor of n coming down, then n minus 1 and n minus 2, and so on. You multiply all this together. That's called n factorial. So I made a little bit of a sprint to get to this next mathlet so that you can see what this looks like. This actually does move. I forgot that I did this. So you can look at a particular polynomial in various places. We've seen the degree 2 polynomial. But you can also adjust the degree. So you're putting more and more terms in here. And you can see it does a great job. It just matches the function really snugly, farther and farther out the more terms that you add. And you can then also move this as you go and kind of see how it slides along, which I think is pretty fun. But anyway, the point is these Taylor approximations are doing some amazing things. Like somehow this function has an information in it for the polynomial to kind of feel out what's happening way the heck over here, even though it's only computing derivatives of the sine function like right around here. It doesn't see the function anywhere else except right at that point. Just like very small window around that point is all you would need to create this orange graph. And yet it's like, you know, doing an increasingly good job of fitting the function farther out. So it's like something really cool about the sine function, that it has information about the entire function embedded in what the function does, like right around any particular point. But anyway, that takes us to 11. There's some more stuff I have here. I'm going to skip it and just leave it in the script. So if you want to see some more discussion about how this relates to machine learning, or some computational stuff about using SymPy to do symbolic math in Python, then I'll just leave that in the script and you can take a look at that later. So like 1 minus 1/2 x squared plus 1 over 4 factorial times x to the 4th. Does that do it? Yeah, there you go. And so that fits over a broader range and sort of curls up a little bit more at the end. And then minus 1 over 720 times x cubed, x to the 6th, that would be the next term. And that fits over an even wider range. And at some point you might want to spread this out to kind of see, kind of like the mathlet, or maybe even more, like, I don't know, 20 or something. Oh, that's not good because the polynomial gets crazy. You can also set y limits to avoid this issue where, because what's happening is when you get far enough away, the polynomial just completely turns loose. Of course, it is a polynomial, sort of like taming a wild animal. You can perform well for a while, but ultimately its nature is what it is. And that's true for polynomials too. Polynomials all go to infinity at their limits unless it's a constant polynomial. So it's only going to fit something like the sine function for so long. Let's see, where does this turn loose roughly? Maybe.
Okay.
But anyway, to do this, so this mathlet is pretty hard coded. It's not, you don't want to write code in the way that I wrote code to make this mathlet happen. If you want to do something like this, but in Python where it's actually sane, then you would use IPy widgets, which is like a Jupyter widget library that allows you actually can't do it quite this way. So the thing that's really special about these mathlets, this technology is called Jsx Graph, and it's in pure JavaScript. It's running in your browser. What's special about this is you can grab everything in the picture. Like I can just like move this label somewhere else if I want. Right. Matplotlib does not do this. You can't do this in Python where you grab a point like that and just move it wherever and things update in a reactive way. That's why I make these things instead of just doing it all in Python. It's a different product. But you can make a slider where you can adjust the degree. So that part can be the same and just like manually set the center. And the way you would want to do that is in SymPy. So maybe I was going to talk about SymPy a little bit, but basically so here's an example of a calculation in SymPy. Oh, I pulled this from sort of later on in the script where we would have already run this thing with T, so it didn't work by itself. But anyway, we can ask SymPy like, hey, integrate T cubed over T squared plus 1 with respect to T. And it knows stuff, like it knows calculus, like the log function comes out, there's no log here. So it's doing some, the stuff you do when you take calculus. It's cool what it's capable of doing. So what you can also do is import series, and then you can call series on a mathematical expression. Like you can say like, okay, like cosine of T, import that too. Cosine of T is a mathematical expression. This is like something SymPy is keeping track of, just like you'd write it on the page. You're not doing anything with it. It's just sitting there, same thing. But then you can call the series function and, oops, mistyped. And it gives you a Taylor series. So remember up here, I did T to the 4th over 24. SymPy knows that. So I'm trying to remember the N is the keyword. Yeah. So the keyword argument here is N. So we can say N equals 26, and it gives us all these terms.
Got it. Okay.
So this produces up to, T to the 24th. And then we could plot that. So you can do what's called lambdify to turn it into an actual function, because this is not a Python function. This is an expression. And you need to turn it into a Python function so that you can plot it. And you have to spell it correctly, which I did not just do. I'm really bad about mistyping lambda. We need to also give the variable for that, like we did a second ago. Oh, you know what? It doesn't like this O expression that comes out when you call series.
Okay.
So somehow we have to find a way to clip off this first 3. There must be an easy way to discard this. But anyway, you'll do that. You'll call lambdify to create an actual function. And then you can plot that function, or you can apply that function. So like if you want to make a squaring function, just to keep life simple, then you can do, like f of x for x in whatever linspace, -3 to 3. And then plot that. So this should work. Yeah, so that's a way to do plotting. In Python, it might seem simpler to just do x squared here, and it is, or maybe just keep the variables the same.
T variable, okay.
Either way, it's fine. In a way, you're like, well, what is lambdify? I don't need that. I can just square things in Python. what's the big deal? But the advantage is, let's say, like in this case, you want to compute some like higher order series. Okay, I wasn't quite able to do it because I need to figure out how to throw away that big O term. What I tried didn't work. But we're like a short step away from like looking at the documentation, discarding that term, and then getting this big polynomial, which we can then convert back into a Python function using lambdify. And that you couldn't do in basic Python without this, without the support of this library. You'd have to write a loop and hard code the values for the series, like what do the coefficients need to be, what are the exponents on t, all that stuff.
Got it.
And
Okay.
with SymPy, you can just say, hey, I want the Taylor series for this function, give it to me. And it's just like, as we saw just a second ago, it's happy to do that in very few lines of code, and it asks for as many as you want.
With the in attribute, you can get as many. Okay, got it.
Yeah, you can just ask for them on demand, or if it's like let's say it's cosine squared you're interested in, SymPy is happy to do that, or like e to the minus x squared or something, or over cosine of x, like it'll do. Sorry, I keep switching between x and t, and right. So like this is like a really complicated function, and it would take you a really long time to work out by hand what all these coefficients are if you wanted this Taylor polynomial for some reason. But with SymPy, you just ask for it and you just get it. So then the only question is, how do I take this thing, which looks very mathy? It's pretty, this is nicer than what you would normally get printing a Python expression.
Right.
But then like, what if you want to actually substitute t in there? You probably want to convert it to a function. You can also use this substitute. I think you can substitute. But that doesn't solve the problem really, because you have to get rid of this term. There must be like a simple, easy way to do that. Yeah, and I can just put that here, and then it'll be on the recording, for folks who want to look at that later. I'll show you like a little bit of what's going on. So suppose you have a function that looks like this, and you're trying to minimize it. So this might seem like sort of arbitrary, but this kind of thing comes up all the time in machine learning, because we have some system and we can describe whether a particular fit is good or bad, but we can't find the best one directly. So instead we work with the description. We say, all right, here's what's good, here's what's bad. And we give a numerical solver the opportunity to go try to look for something that's good using general techniques. And so you can imagine the landscape here. It's usually higher dimensional because the model will have more than one free parameter. Here we just have left and right. That's the only parameter we can control. But you'll have a higher dimensional analog of something like this, where you might move around and you might be like, okay, nothing changes. It's all equally bad. And then at some point you might find like, okay, this is better. And you also know which way to go. So you can kind of feel out the bottom of this well. And then you kind of know when you settled into the bottom of it, you're like, okay, this is pretty good. I'm going to return this as my fit that I found. But then, there might be a lower one over here that's even better. Like this is lower down than that is. It's better. But it's also hard to find, because you might be searching around over here, and you never find it. You have to actually try an input value that's starting to take you down, and then you need to be careful, because if you step in such a way that you shoot way to the right, you'll miss it. You have to kind of gear down to kind of get way down in this narrow crevice. If you're kind of feeling out like, okay, I'm going to move left and right a little bit to try to find the bottom of this thing. And so these are really different. This is like good and easy. Like as soon as you get nearby, you're going to settle in pretty quickly. Whereas this is much harder and requires more caution, both for finding it and for getting down to the bottom once you do find it. At some point, real work has to be done to kind of separate these, to figure out what to do to actually get down into the bottom of a narrow crevice like this. I'm not touching on that so much here, because it's really about sort of just like, how do you distinguish these cases? Like, what's the difference mathematically between a spike like this and a broader well like that? And the difference is the second derivative. And you can see that if you fit a Taylor polynomial to this function. So I don't have this set up in the Mathlib, but here it would be almost dead flat. Here it would be nicely hugging this in a quadratic way, but it would, it wouldn't be super steep. It would be somewhat steep, but, fairly gentle of an arc here. And over here, it would be extremely steep because it would be matching this graph through this area. So it would be just like a super sharp parabolic spike here. And that's telling you that the second derivative, which is dictating the sort of curvature, the curviness of your approximation of the function at each point, the second derivative is super big here and it's lower here. So that means if you have a good way to estimate second derivatives, which we'll also talk about in 1010, and there are good ways to do that, then you're able to tell just from looking at that second derivative, like, okay, over here, here's what's going on, and over here, this other thing is going on, and you can understand the differences. And also the story gets much more interesting in higher dimensions where you don't just have like, kind of flat versus spiky. You have that sort of behavior, but in lots of different dimensions and potentially with a different orientation that's not just along the coordinate axes. Unwinding all of that story is pretty fun and cool, but it starts with this idea of Taylor series and looking at a quadratic approximation around a particular local minimum.